Hello, we continue with semi-definite systems. Semi-definite systems are a special case in multi-degree or two-degree of freedom systems. As you can see here, for an example, here we have two railway cars of masses M1 and M2 can be modeled as this figure here. This is a semi-definite system, and I will explain what we call it semi-definite. Or another example, here we will have two rotors of mass moments of inertia J1 and J2, as you can see, connected by a shaft can be modeled again as this system, similar to mass and one spring. Here we have, instead of two mass, we have two mass moment of inertia J1 and J2 with one equivalent spring KT, which is a rotational spring. They are connected to each other. These type of systems are called semi-definite or unrestrained systems, and the characteristic of this case is that they can move as a rigid body. As you can see here, this system includes M1 and M2. I mean, if we separate, this system can move as a rigid body. I mean, M1 and M2 can uh, move to the right or left with the same velocity as a rigid body. Or here, these two shafts, this system can rotate without any vibration as a rigid body can move. And all of these systems, which we call them semi-definite or unrestrained systems, they can have a mode or a mode shape of like a rigid body, and they can move as a rigid body. But at the same time, when they are moving as a rigid body, these mass, for example, M1 and M2, when they are moving as a rigid body, at the same time, they can have vibrational motion with respect to each other and relative to one another. They can vibrate, but at the same time, they are moving as a rigid body. In vibration and in the equation of motion, we will have one phenomenon that will result in this rigid body motion or this phenomenon. And you will see in the next slide, you will see that when you extract the equation of motion, there is an important difference between the equation of motion for this type of systems and other systems. So from the equation of motion in terms of mathematics, we can conclude the rigid body motion for these systems. So we need to extract the equation of motion. If you extract the equation of motion for example, for the first system with two masses connected with the spring K, and write the Newton's second law for the first mass and second mass, you can extract these two equations. The first equation is the Newton's second law for the mass M1, as you can see, and the second equation is extracted from the Newton's second law for the mass M2. As you can see here, in the first equation, we only have x1 double dot, but we have x1 and x2. So this system has coupling of static terms, or we have static or elastic coupling, but there is no dynamic coupling in this system. So this is the equation of motion. The next step, we need to solve this equation similar to the previous examples and previous section. We need to consider the response in a harmonic form to obtain the free vibration response and form the characteristic or frequency equation. If we assume the response in this form, which is a harmonic with frequency omega, and this omega will be obtained as the eigenvalue or the natural frequency of the system, now we can substitute into the equation. I mean, instead of x1t, we can substitute x1 cosine omega t plus v1, and instead of x2 we can substitute x2 cosine omega t plus phi 2. Only we need to calculate the second derivative of x1 and x2, which you know the second derivative of this term is minus omega squared x cosine omega t plus phi. So x1 double dot in fact is equal to minus omega squared times by x1. And now we can substitute and simplify and extract the characteristic equation by finding the determinant of the coefficient matrix. The determinant of coefficient matrix, which is the frequency equation, results in this equation. In this equation, you can see the roots of omega are 0 and one non-zero component. Here you can see the first frequency is 0, as here we have omega squared multiplied by this term. Omega squared multiplied by this term, it means that one root is 0 and the second root will be obtained from this term, and it's equal to this term here, calculated here. So the first frequency or the lowest frequency is 0, and this is the characteristic of the system which we call them semi-definite systems or unrestrained systems. So in these systems, the lowest frequency is 0, or they have one zero natural frequency, and this 0 is due to the rigid body motion. So anytime when you extract the equation of motion for your system and you solve the equations and you find 1,0 roots for the characteristic equation or for the natural frequency, it means that you deal with a semi-definite system. Okay, so this is the characteristic for this type of systems. And for example, here you can see one example. We have two identical circular cylinders of radius r and mass m each. They are connected by a spring as shown. Determine the natural frequencies of oscillation of the system. So we need to extract the equation of motion. For this case, from dynamics, you know, when two circular cylinder they are moving on a surface, here definitely there is no slipping on this surface, because if we had a slipping, the degree of freedom was more than 2. But when we assume that this system is moving without the slipping, definitely the degree of freedom is 2. We consider 2 degree of freedom as theta 1 and theta 2. Here we call it, this angle is theta 1 and the second one is this angle is theta 2. From dynamics, you know that when we have motion without the slipping at this point, we can assume that this cylinder has a pure rotational motion about this point. For example, we call it O1. And for the second cylinder, again, when we assume that there is no slipping in the motion, so at this point, which we call it O2, we can assume that this cylinder has a pure rotational motion about point O2, and we can assume that the cylinder is pinned at this point. Now, if you want to use the Newton's second law, the best option when you have a pure rotational motion is writing the moment equation about the fixed point of rotation. So for the first cylinder, we can write the moment equation about this point O1. And for the second cylinder, it's better to write the moment equation about point O2. When you write the force equation and plot the free body diagram, I mean, for example, for the first cylinder, we will have two reactions at the connection point. We have the weight of the cylinder, and also we have one force due to this spring, which is K times by the displacement. But for the spring, you can see that both ends this edge and this edge, both of the edges are moving to the right. So if we assume the direction of the force is to the left, something like this that I plotted here, so the force in the spring is K, the displacement of this point minus the displacement of this point. If we call it, for example, point A and point B. So the force in the spring, according to this assumption for the direction of the force, the displacement of A minus displacement of B. So we call it XA minus XB. Okay, so this negative is because both point A and B, both of them are moving to the right. So it means that at point A, we are at point A, the spring is under pressure. I mean, point A is putting a pressure on the spring, but at point B, we are pulling the spring. I mean, point B is pulling the spring. So here we assume that the force in the spring is compression. So when you assume that the force is in compression direction, point A, the displacement of point A will increase this compression, but the displacement at point B, which is to the right, will decrease this compression because we assume that point B is going to the right. So it will pull the spring and it will decrease the compression in the spring. So we consider a negative. If we assume that theta 2 was to the counterclockwise direction and point B was moving to the left, then we assume that XB is positive, so it was plus XB. But here we assume that theta 2 is in clockwise direction, similar to theta 1. So both point A and B, both of them will move to the right, and point A will press the spring, but point B will pull the spring. So we will have one negative here. And we know that XA and XB, because both cylinders are rotating about point O1 and O2, so the XA can be easily substituted by R times by theta 1, and XB will be substituted by R times by theta 2. Because theta 1 and theta 2 are small, we extract the equation of motion for a small deflection, in this course, because we want to extract the linear equation. So this is the free body diagram for this first cylinder. For the second cylinder, we have the same procedure, the same scenario. You can extract the free body diagram, and when you write the moment equation about this point, assume that we extract the moment equation about this point. When you write the moment equation, the weight, we call it W, this W, because pass through this point, so it doesn't have any moment, so it will not it won't be appeared in the moment equation. And these two forces, the reactions at the point O1 or at the pin connection, of course the imaginary pin connection, these two forces, because both of them pass through this point O1, so they will not appear in the moment equation, and only the force due to the spring, this force K times by XA minus XB, will appear, and the moment is equal to this force multiplied by its arm, which is R. This is the arm of this force when you are calculating the moment about this point O1. So you can write the moment equation for the first cylinder and second cylinder, and we can extract the equation of motion. Okay, as you can see, this is the first cylinder equation. Kr squared theta 1 minus Kr squared theta 2, and we have Jo theta 1 double dot, which Jo is the mass moment of inertia about this point O, which we call O1. Okay, because we assume that this is a fixed point of rotation, and from dynamics, when you are writing the moment equation, I mean the moment about point O, it's equal to Jo theta double dot or alpha. Okay, when this point O is the fixed point of rotation, we can write in this form. But if this point was not the fixed point of rotation, here we will have an addition term, which is ma times by d, which a is the acceleration, d is the distance between point O and the mass center, and m is the mass of the rigid body. And here, instead of jo, we will have jg. Okay, so here, but this point is the fixed point of rotation, so we only have the moment about this point. It's equal to j o theta double dot. Okay, so easily you can extract the equation of motion for both cylinders. And as I told you, jo is the mass moment of inertia about this point, which is equal to the mass moment of inertia about the mass center for a cylinder, which is half mr squared plus md squared, which in this case, d is the distance between the mass center here and the point O, and here is equal to r, so plus mr squared, and finally it's equal to 3 over 2 times by mr squared. Now we can write in matrix form. This is the matrix M and this is the matrix K. Again, you can see that we don't have dynamic coupling and only we have a static or elastic coupling in this system. So to extract the natural frequencies of this system, we can form the matrix of the coefficient K minus M omega squared. And if you find the determinant of this matrix, you can obtain omega 1 and omega 2. So we can form the matrix K minus matrix M multiplied by omega squared. You can form this matrix, and the determinant of this matrix must be equal to 0 to extract the characteristic or frequency equation. Now, if you solve this equation, you will see that, and simplify this, this is the characteristic equation. Again, we have omega squared multiplied by this term. Omega squared must be equal to 0, the first root. So the first root is 0 and the second root is a non-zero term. So again, you can see this is a semi-definite system because we have 1, 0 natural frequency. And also from the physics of the problem here, if you look at this, you can see this system can move as a rigid body. I mean, both masses can move as a rigid body without any vibration. I mean, for example, when this mass is moving with velocity v and at the same time the second mass is moving with the same velocity, so the relative velocity between this point A and B is 0. So it means that both masses will moving as a rigid body, and this spring will not insert any force to the springs, okay, because it's moving with as a rigid body or as a rigid rod between a connection between two cylinders. So this is from the physics of the problem, but from the equation of motion, we extract the natural frequencies and we obtain that the first natural frequency is 0. So it means that this is a semi-definite system. Okay. Another method to obtain the response of the systems subjected to, in STOF systems, you saw that when we deal with a system which is subjected to a non-periodic or an arbitrary external force, when we cannot extract any harmonic form for the external force, usually we use other methods. In the STOF system, we use, for example, convolution integral and Laplace transform. Here we can expand the Laplace transform method for the 2-degree of freedom systems. If we can solve the equation of motion for a 2-degree of freedom system, we can solve it and obtain the response, the particular response, of course, by using the Laplace transform. Here, in this case, if you use the Laplace transform, you can directly find the particular response or the steady state response for the system. But if you want to extract the natural frequencies, be informed that this method is not suitable. I mean, you cannot obtain the natural frequencies or mode shapes. And if you want to extract the natural frequency and mode shapes, you need to use um the free vibration analysis, similar to the previous section, and you need to consider that the non-homogeneous terms f1 and f2 are equal to 0, and then you can obtain the natural frequencies. But here in this case, we deal with a system, a damped system, and we want to obtain the response of this system subjected to the external force F1 and F2 with non-homogeneous terms by using the Laplace transform. As you know, the Laplace transform needs the initial condition. For this case, we assume that the initial condition is 0. You know that when the initial condition is not 0, the solution procedure is the same, but we will have some additional term. But here we assume that the initial condition is 0, so we can find the Laplace transform of the equations, or we can convert them into an algebraic equation by using the Laplace transform and move the equations from the time domain to the Laplace domain. We know that the Laplace transform of x1 double dot is s squared times by x1. Laplace transform of x1 dot is s times by x1. For x2 dot is s times by x2, and for x1 and x2 is x1 or uppercase x1 and uppercase x2. And for f1, the Laplace transform is assumed to be uppercase f sub 1. So you can find it, and now we will have, instead of in SDOF systems, we had only one algebraic equation that we solved it and obtained the response in the Laplace domain. But here we have a system of two equations with two unknowns. The two unknowns are x1 and x2, as you can see, a system of two coupled algebraic equations. You can solve these two algebraic equations easily by different methods. The first equation here you can see is a coefficient multiplied by x1 plus another coefficient multiplied by x2, it's equal to f1. The second equation is again a coefficient multiplied by x2 plus a coefficient multiplied by x1, it's equal to f2. We can solve this system. I mean, for example, from the first equation, you can assume a relation and you can extract a relation between x1 and x2. For example, if we assume that the coefficient of x1 is c1 and the coefficient of x2 is c2, we can extract that x1 is equal to f1 minus c2 multiplied by x2 divided by c1. Now you can see x1 is a function of x2 and f1. In the second equation, you can substitute, instead of x1, you can substitute this term. Then you will see that you have one equation with one unknown, which is x2. And then you can solve it and obtain x2 as a function of f1 and f2. And once the x2 is obtained, you can substitute in this equation and obtain x1. So it's up to you. You can use different methods, but here I will review the method of Cramer's rule. Using this method in the system of algebraic equation, you can easily find the response from these grammar rules. And here you can see x1 is equal to d1 divided by d, and x2 is equal to d2 divided by d, which d1, if you form this matrix, which its first column is the non-homogeneous vector, as you can see, f1 and f2, because we are calculating the x1, and the second column is the coefficient of x2, and here this x2 in the second equation. I mean, if you write this equation, this system of equations in the matrix form, you will have a matrix M, or we call it, for example, matrix C multiplied by x1 and x2. This is the grammar rules, just to remind you, and it's equal to f1 and f2. Okay, this is the equation, these two equations in matrix form. If you write it in matrix form, you can extract this form. This is the matrix C. For example, the first component in the first column of this matrix C is the coefficient of x1. The first component in the second column is the coefficient of x2 in the first equation. The second component in the first column is the coefficient of x1, this term, and the second component in the second column is the coefficient of x2, this term, in the second equation, and it's multiplied by x1 and x2, and it's equal to f1 and f2. To obtain d1, you can move the first column of matrix C, this matrix, and instead of the first column, you should substitute the matrix f1 and f2. To find d2, you need to form this matrix, which its first column is the first column of matrix C, but the second column is substituted by the vector f1 and f2, as you can see. Now you can calculate the determinant of this matrix. This is d2. And finally d, which is the determinant of matrix C. If you calculate the determinant of this matrix C, this is called d. And if you substitute here, you can find x1 and x2. This is the Cramer's rule, or you can use the traditional method as I explained. You can solve the first equation and obtain the relation between x1 and x2, and then you can substitute and find x1 or x2 and then find the other one. So you deal with a system of two algebraic equations. We convert or ordinary differential equations into the algebraic equations, a system of algebraic equations, and you can solve these algebraic equations using any methods that you prefer. It's up to you. For example, here we want to find the steady state response of the two masses of the two-story building frame shown in figure under the ground displacement yt, which is equal to 0.2 times by sine pi t. So this is the yt, the displacement of the base. Assume the equivalent stiffness of the lower and upper columns to be 800 and 600 respectively, and the mass of each the mass of each story M1 and M2 are equal to 50 kilogram, and the external force F1 and F2 here in this example considered they are 0. So we deal with a system with base excitation or base motion, which is called yt. This yt is harmonic, and here there is no damping in the system. You can find the response using the previous method. I mean, without the Laplace transform, you can easily find the response of this system because yt is a harmonic with frequency pi. So you can consider the response exactly like this. X can be considered, for example, xi, of course, it should be a small x, lowercase x. Xi is equal to xi sine times by pi t, and then you can substitute and find this amplitude for x1 and x2, and you can use the previous method. But here we want to use the Laplace transform. For this purpose, we need to extract the equation of motion. Of course, for the previous method, you also need to obtain the equation of motion always. So we extract the equation of motion and we will solve this system. If you write the force equation and assume that we have two springs, two equivalent springs K1 and K2, which is connected the mass M1 to the ground and the mass M2 to the M1 respectively, we can write the equation of motion easily for both masses. For the first one, M1, if you write the Newton's second law and assume that this mass M1 is connected to the ground with the spring K1, and also there is a connection between M1 and M2 with the spring K2, you can easily write M1 x1 double dot, which is the acceleration, is equal to the summation of the force acting on this mass in, of course, in horizontal direction. So you can write, we will have a force due to the spring K1 and another force due to the spring K2. The force in the spring K1 is due to the displacement x1 and y, which this y is the base motion, and it will appear as the non-homogeneous term in the equation of motion. And if you write the force equation for M2, then write the Newton's second law for the mass M2, you can conclude that the mass M2 times by its acceleration is equal to the summation of the force in horizontal direction. And for this mass, only the spring K2 will affect, and it will appear in the equation of motion, and we will have K2 x2 minus x1. So this is the equation of motion. If you write in the matrix form, you can see there is no dynamic coupling because matrix M is diagonal and matrix K is a non-diagonal matrix. So we have the static coupling. The external force Ft is equal to K1 times by Yt, or 0.2 times by K1 times by sine pi t. As I told you, from now you can use the previous method to obtain the response for this system, or you can use the Laplace transform. Similar to the single degree of freedom systems, you can obtain the response with different methods. Here I used the previous method. I consider the response in this form, x1 and x2 multiplied by sine pi t. So the acceleration, or x double dot, is equal to minus omega squared, which omega is equal to pi here, times by x pt. So we have minus pi squared multiplied by this term, as you can see here. And when you substitute in the equation of motion, you can easily obtain x1 and x2. So we have these two algebraic equations, as you can see, matrix K minus matrix M. Of course, this is a matrix as well, so it will be this form, multiplied by omega squared. It's equal to the vector F. And this omega in this case is equal to pi, so we can find easily x1 and x2, which is the inverse of this matrix multiplied by the vector F. So we have one example. We can continue this for next week. And for today, I think it's enough because this example needs more time. And we can continue next week. So we will have a 10 minutes break, and again we continue with tutorial. Okay, thank you.